video, I'm going to introduce you guys to kinetic and static friction, and I'm going to do it through a very small example. So let's say that we have a particular block which is lying on a very rough surface. So that's your block of mass m, and this is your rough surface right here. And let's say you wanted to try and move this block by applying a force P on it. So here's the block, here's the direction of your force you're applying, and it's got a magnitude of P, and the block is a mass of m. Right, well first we know that if you try and move an object, like say a table on a carpet, there are times where it's unsuccessful. If your P value, or like say you don't push the table hard enough, right, the table will actually just not move, and that's because there's a coefficient of static friction which is high enough to the point where it overcomes the force that's being applied on it. So, and we can express this mathematically too, and I think that's the easiest way to actually understand this, but as long as you have the basic intuition behind it, I think that's a good start. So we know that there's going to be two external forces acting on it. One's going to be the force due to gravity, that's going to be mg right here, and there's also going to be a normal force acting on this object as well, n. That's from the carpet acting up to make sure that the block doesn't just accelerate into the ground or anything like that. Okay, well, there are actually two situations that are possible here. We know that if P is greater than 0, right, that means that there's going to be a tendency to try and move the block to the right, right? And we know friction, or just resistance in general, will always try and resist, or will have a vector in the opposite direction towards what's trying to be applied on it. So we know that in this particular case there will be a friction force to the left, because there's a tendency to try and move the block to the right. So this vector right here is going to denote my friction force, and we found experimentally that your friction force can be determined by mu s n, where n is your normal vector, which I've drawn above, and mu s is your static coefficient, right? And this is going to be a number between 0 and 1. So let's say we wanted to now analyze this mathematically to have a more in-depth understanding of what happens. So we know that the sum of forces in the y direction are going to be equal to 0. Actually, let me just draw a small little set of axes just here. So this is going to be your x-axis, and this is going to be your y-axis. So you know the sum of forces is always going to be equal to 0 in this particular case, because even when you push the block to the left or right, regardless of whether it moves or not, the block is not going to accelerate upwards or accelerate down. It's going to be stuck on this carpet or this rough surface I've drawn here. So this will always be the case. Fy, the sum of forces in the y direction are going to be equal to 0, which implies that the sum of forces up are going to be equal to the sum of forces down. So that means n is going to be equal to mg. That's going to be a useful formula. That's going to be a useful formula later. And now let's try and analyze what happens in the x direction. Well, assuming that the block doesn't move, that means that the sum of your forces in your x direction are going to be equal to 0 too. The sum of forces in your x direction are going to be equal as well, right? Which implies that P, in this particular case, is going to be equal to mu s n. Or if we like, we can rewrite that as mu s mg in this particular example. Righto. But let's also evaluate what this means some more. This right here represents an upper limit for what P must be equal to in order for the block not to move. We know that if P was even less than this, but still greater than 0, then the block wouldn't move either, right? So in fact, we can actually say that if P is less than mu s mg, then the block will not move to the right. So that I'll just put then no movement meant to the right. To the right. Righto. And don't forget, this is also assuming that P is greater than 0 as well. Right? Because if P was less than 0, that means that's essentially like saying that you're going to have a force P that's being applied in the opposite direction. In fact, let's consider that case now. So we'll call this case 1. This is for P is greater than 0, right? So in other words, there is actually a force acting towards the right. But let's now consider a second case. Let's consider a second case where you're also having a block which has an external force P being applied to it, but let's consider the case where P is now less than 0. So 2P is less than 0. Well, we know there's going to be a force due to gravity just like before, mg. The normal force is going to be the exact same. It's also going to be mg because the sum of forces in the y direction are going to be equal to 0 too. But in this particular case where P is less than 0, that's essentially like saying instead of pulling this block to the right, we're going to push it to the left, right? So in other words, our friction force now will actually be in this direction, because remember, friction always opposes the attempted direction of movement. So this will be mu s n right here. Alright, so, and I probably should have drawn the floor just there so I don't confuse you. There is static friction here, and just as a brief aside, friction is actually caused by small little grooves in the surface, because no surface is actually completely flat. There's small little grooves, and we managed to analyze this experimentally, determining that the friction force is mu Sn. Anyway, that's a small aside just there. So now let's go into analyzing the second case a little bit more. Well, I'll just draw a 2 here to indicate the second case. Well, we know as well that n is equal to mg, right? The sum of forces is in the y direction, well, that's still the case. But the sum of forces in the x direction, let's see, for no movement to occur, the sum of forces in the x direction have to be equal to 0, right? Which implies that P plus mu Sn must be equal to 0, right? Because P and mu Sn are in the same direction now. So that implies that P is going to be equal to negative mu S mg, right? Which is very similar to the result we got here. But let's also consider what happens. This is a lower limit for P, right? If P was any less than this, right? If P was acting any less, which means it would be acting stronger in the left direction, that means it would overcome static friction, which means that it would start moving. So in other words, we can say if P is greater than minus mu S mg, then no movement to the left. Right? Let's see if we can understand this right here. So if P is less than the static friction moving to, if P is less than mu S mg, that means there's going to be no movement to the right, assuming P is greater than 0. That was our first case scenario. And in the second case, when P is less than 0, if P was greater than minus mu S mg, that means there would be no movement to the left either. So if we wanted to create an inequality which described every single range of value P could have such that there was no net movement of the block, we could just stuff these two equations together to try and form something. And let's see if this works. Let's see if this describes everything we've got above. If we've got minus mu S mg is less than P is less than mu S mg, then there's going to be no movement. Let's check if that satisfies equation 1 and equation 2. Well, mu P is less than mu S mg. Yep, that's this right-hand side of the inequality just there. And P is greater than minus mu S mg. That's the left-hand side just here. In fact, what you could do is you could even like draw this on a number line, just map out every single value of P right here. So this is a one-dimensional axis right here, and this could be, you know, mu S mg, and this could be minus mu S mg. And in fact, the values for which P doesn't, and this would be 0 right here, and the values for which P doesn't move would be in between here and here. This would just be for the first case, and this would be for the second case. Don't get too hungover about this, just try to understand the mathematical implications of just summing all these inequalities together, simply so we can understand that for the block not to move, this has to be obeyed, this small inequality just here. So in this particular example, this is what needs to be satisfied for the block not to move. However, if P didn't fit within inside this inequality, that would mean that the block is moving to the right or to the left. And I'm running out of time here, so I'll explain exactly how you calculate what will happen if this inequality isn't told, and that's using something called a kinetic static friction coefficient. Anyway, I'll catch you in the next video.